Hi, everyone. We're Team C++. My name is Liam.
I'm Ziad.
I'm Henry.
I'm Zen.
And we're here to make augmented reality immersive. So what do we mean by this? So we love sci-fi like everyone else does. And I don't know about you guys, but when I see Iron Man on a movie pulling up a virtual screen and operating his computer with his hands, or someone speaking to a hologram, I would love to have that sort of technology in our world. And in fact, that sort of technology already exists, and it's in the form of augmented reality. So augmented reality is a technology where a virtual object is projected into the real world through some sort of interface, like a headset or a phone screen, like this sort of image here. As you can see, it's a virtual table next to that real lamp on the left side. There are holes in the wall, and enemies are trying to come through and attack the crystal. This next example, the actual city on the table that's not through the iPad screen is an artist rendering, but you would be looking through some sort of a screen, and you'd project a virtual object onto a real object, like this pet in an office room. However, there's something that's missing about this that's not quite the sci-fi level that we're looking for, and it's that it's not immersive. And Zito will talk more about why that is.
Thanks, Liam. So the reason we think augmented reality is currently not immersive can be explained with an illustrative example. I'm sure you all know about a little game called Pokemon Go. And surely when I fired up the game in my backyard the first time, I was expecting this little creature to be, immersively embedded in my backyard. But it was just sitting awkwardly between grass blades, and it just didn't feel realistic enough. You can imagine a more creative scenario where you're sitting next to a tree, and this little creature, let's say it has bug-type features, and it would be crawling up the tree instead of just sitting there doing absolutely nothing. Or if it had bird-like features, it would be sitting on top of a branch, right? And the reason AR developers can't really do this right now is because AR development frameworks just don't offer the capabilities that enable you to do this. And what we mean by that is that currently AR development teams sort of only have a couple of interesting detection features, such as surface detection and wall detection, but that's it, right? They can't really detect interesting objects. They can't know where they are. The image is just basically just pixels and colors, and then here's the wall, here's the floor, and that is it. But actually, detecting objects is sort of like a solved problem. We can do that. We can detect bikes, people, cars, chairs, cups, really like a varied list of objects, but it's just not integrated with current AR development frameworks. And this is what we want to do. And also the reason why the industry doesn't do this right now is, go ahead.
Keep going.
Yeah, actually what we mean by that is that basically you have this image of a room, and now you can know where the beds are relative to each other, the chair, what it is relative to everything else. And in the industry, the challenge can be basically summarized in three things. The first two, battery life and compute power. What we mean by that is that doing all this graphics rendering and also detecting objects at the same time requires a beefy computer, but users don't really have that. And also AR developers don't necessarily need this at this point in time. And also the third sort of challenge is ease of use. And so enabling scene understanding and object detection in an AR development framework requires that game developers really know how to use computer vision and what that means, and really know how to operate these algorithms. But necessarily it doesn't mean that it has to be in their skill set. So an AR development framework that has scene understanding in it has to be very easy to use. And this is where our product sort of comes in. But enough talking about what we wanted to do. Here's what we actually did. In the beginning, C++ does this mesh building, spatial mapping, and also depth sensing. And this is where that blue stuff comes in. So this what it means is that now scene understanding understands where things are in terms of depth, but it doesn't really recognize objects. But after that's done, we send the images, and we actually detect specific objects in the room, and that's where you see the flowers on top of the vase, the flames on top of the bowl. We replace targets, we replace clocks with targets, and we also label all sorts of other things that we're actually able to detect. And you can interactively play around with these things in real time. And yeah, and so this snapshot is sort of the list, or a subset of the list that we can, of things that we can actually detect, bowls, dining tables, mouse, cell phone. We replace a cell phone with an Apple because it's iPhone or whatever, but we also have an animated mouse character that actually replaces a computer mouse, flowers on a vase, and so forth. And so spatial mapping, how it works, that again, you have this mesh, and after that, you send the image, and we're able to overlay virtual objects on top of them in real time. And now Zen will go in depth into our technical approach.
Thank you, Ziad. So to make scene understanding a reality, we leverage 3 key technologies to make it possible. First, we leverage cloud computing to offload the expensive computational tasks, such as deep learning, to the cloud, making our platform and making our framework platform independent. What that means is if a device can connect to the internet, it can run our C++ framework. We also leverage deep learning object detection to detect the objects in the current scene, and that's the computer vision part. And we use game engine, Unity in our case, to build easy-to-use APIs for game developers to leverage and use out of the box. They will get a list of objects that are detected, and then they can overlay gaming content on it. And our chosen hardware platform is this Z Mini camera, which is the camera that are attached in the front, a dual lens depth camera that it can detect, that it has depth perception, and we attach that to the Oculus Rift virtual reality headset, which displayed the gaming content. Now I will walk you guys through our whole workflow. First, the camera captures the image and depth data, packs it up, and sends it to the cloud, where it is passed through an image processor, an object detection algorithm, and we serialize the detected objects and send it back. And these are the cloud computing side. And from the gaming side, after the objects are received, combining with the spatial mapping that we demonstrated before, every one of these objects will be localized in the current real world, where game developers can just overlay 3D contents on top of them. And these overlaid contents will be displayed onto the Oculus Rift headset. And that's our complete workflow. Now I will pass it on to Liam to talk about our evaluation and results.
Thanks so much, Zen. So for our criteria, we really zeroed in on 3 main points to assess how well we did our job. The first one is object detection variety. So how many different objects can we detect in the scene? Do we ever mislabel them? Second thing, cloud computing latency. Naturally, since we're offloading things to the cloud in real time, how long does that process take? How long before we send an image and receive it? And that translates in our game to how long does it take for an object appearing in front of you before it is recognized by our system? And the third metric, which we believe to be the most important, is the frames per second count. Now, frames per second is how many pictures are shown to the user, basically the fluidity of the movie. But this is especially important in virtual reality and augmented reality, especially in a head-mounted display, because if you have a low frames per second count, the user will get sick in virtual reality. And so if our Scene++ code makes the frames per second count go under that level, we did not accomplish our job, regardless of what we wanted to do. So as for the object detection code, this was the slide that we shown before. So the object detection framework, a lot of the metrics are quite complicated, so it's difficult for us to explain during this presentation as to how accurate it is. But needless to say, this is the standard in the industry right now. This is mask RCNN. And in our experience, the resolution that we were sending images at, we were sending at 1/4 to improve latency, didn't severely affect the performance of the object detection algorithms, and most of these objects were correctly detected and localized. The full list of objects for mask RCNN is here. We were able to test a lot of these. We couldn't get our hands on an elephant, but otherwise a lot of these were, yeah. Cloud computing latency, we've done a lot of tests. There's a lot of numbers. The point is that under 1 second. So it's pretty fast. This is the clip from earlier video. These targets, we're not actually remembering where the targets are in the scene. We're actually redetecting them when they are hit by the gun there. So it's a good demonstration of how fast these things are redetected. And like we mentioned, it's less than 1 second. And the most important metric, the frames per second. So the Z Mini demo, as Zen mentioned, the Z Mini is the camera we have in front of the Oculus Rift. The baseline demo, their game that they came prepackaged to show their AR capability had 47 frames per second. And a lot of these modern games try to hit 60 frames per second, and 30 frames per second is pretty much the baseline for what would be considered playable. And so 47 was kind of a rough starting point. But our Scene++ performance impact in total was only 6 frames per second, which we were blown away by. It exceeded our expectations on how little of a performance impact it had, and that's mainly due to the fact that once we send one image to the cloud, we don't have to constantly send these images. It's tagged in our spatial map. So we were able to save a lot of that computation power, and the only impact that C++ has is that initial sending of the 1/4 resolution image. So as for our next steps, so while we were doing this project, Microsoft announced their HoloLens 2. Now, like I mentioned earlier, the Z camera had a base frame rate of 47 frames per second, and one of our main theories as to why that is because the camera at the front of the Oculus has to go through a USB, through the computer, back up to the Oculus in order to be displayed, which that sort of latency adds a lot of issues. However, the HoloLens 2 has a built-in integrated camera through the headset. And so that sort of latency will greatly improve the capabilities of not only the hardware, but of our C++ framework as well. And so since the industry is building this sort of hardware, we feel like we're kind of on the right track with our thoughts that this is where the industry is going. And as for more complicated computer vision things, Zen wants to talk about his stretch goal for this.
So one of our stretch goals for this project is to integrate post-estimation. One of our advantage of offloading our computational tasks to the cloud is we can integrate these advanced computer vision tasks really easily. And we want to integrate post-estimation. What is post-estimation? Right now, we can localize objects in the real world. We know here's a bottle here, but post-estimation gives you the richness of data in terms of you know where this bottle is facing, the orientation and rotation of this object. And these kind of information given to the game developers can let them to build a much more immersive games. But due to the limitation, this post-estimation is still an active research area, and we do have it integrated, but the performance was just not as we desired, so we did not include it in our final demo.
Yeah, and as Zen mentioned previously, we chose Unity 3D as our main game engine to basically overlay the game content. The reason for this is that it's very popular, it's free to use, a lot of independent developers actually use it, and it's actually well integrated with AR development frameworks. And so that's basically done, but we would love to, if we were able to, also extend this to other game engines such as Unreal 4 or any other game engine really. So that's basically on our priority list. But that is it, and now we'll take questions. Thank you. Yeah.
So you were saying 1/4 image. So what's the transmit rate required? What's the bandwidth rate required to achieve reasonable performance, given your reduced pixel?
So basically, the image is 1/4, right? And basically, what is the bandwidth required for us to make this in real time? Is that the question?
So you're looking around the room, you're taking images, you're sending it to the cloud, processing and coming back. Mm-hmm. What sort of connection do you need, local internet connection do you need to make this effective?
So one of the things that we wanted to make sure this C++ supported was if we had some sort of spotty internet connection, or maybe it wasn't as constant as we would have liked. And so one of the ways we got around this was, like I mentioned earlier, when we were to send an image to the cloud and tag it in the spatial map, then it stays permanently. So even if the bandwidth is very low and it takes a long time for the image to be transferred, it only will affect the initial tagging of the object. And so once that object is tagged, it might go from maybe half a second to like 2 or 3 seconds if it's really bad internet connection. But once the object is tagged, it's tagged forever. And so we do not have to re-tag it. So, yeah.
Mm-hmm.
I'm just curious if you looked at, for example, robots. Because I've seen this kind of problem in robot movement and handling type things where they need to be able to identify obstacles or pick things off cables. Did you learn anything looking at that, and do you see that this might have applications in that area?
Yes, so our framework is pretty independent. So we use augmented reality because it's very tangible and it's very easy to build a demo around it. And this framework can definitely be used in robotics because these two areas have a lot of similar tasks, such as grasping, you need post-estimation, you need object detection, and definitely robotics is one area that this can definitely be applied to, but we chose augmented reality because all of us have AR experience, and we just really want to build an experience around it.
Thank you so much.